Because if you look hard enough, what you'll see is you'll learn a lot about David. You'll learn that David is a very busy person. So busy, he doesn't have time to fill out this thing on the schedule. David is a co-founder of a consultancy that helps companies scale out well. And this talk is about reactivity, but usually at a conference, when you hear the word reactivity, when you hear like JavaScript and reactivity in the same sentence, like I feel like most people I talk to go like towards the direction of stately redux, something to do with like UI reactiveness. React is not a reactive library, this kind of thing. There's a new what's solid.js, right? This is why I'm excited for this talk, because this talk is about reactivity, but like on the server side. In fact, David mentioned to me earlier, he said, hey, you remember when you did that Zada drawing that I did earlier? He said with like pushing from Kafka to Elasticsearch, he's like, that's the kind of reactivity I'm talking about, okay? And so with that, I'm really excited for this talk. I hope you are too. Show me, how are you feeling? Are you ready for the next talk? Yeah. It's good. We have please extend your warmest welcome to David Leitner.
Can you hear me? You cannot see the slide. Ooh, give me a second. I made a very bad decision to do all this stuff in JavaScript, so it's yeah. Oh, it looks a little bit strange, doesn't it? Give me a second. Chuck. Yeah. Cool. So I think this will be kind of tricky to get this done in 30 minutes. So maybe we'll use a little bit of your break. I hope that's fine. I'm talking about a reactive mindset, software that scales. Yeah, I love to give talks, titles like this, because, you know, the train to Vorarlberg is quite long from Vienna, and then you have, 8 hours time to think what you're talking about. So you always need to give some kind of, buzzworthy title. Because usually when people ask you to talk at conferences, you're not really sure what you will talk about then, right? It's usually happening months before. And I usually talk about reactive systems and reactivity and all the stuff which was already mentioned. And I would like to tell you a little bit about scaling with reactivity, because that's basically what I'm doing, as already mentioned. I'm a co-founder of a Viennese company. We're quite small. We're around 30 people now. And what we actually most of the time do is we help scale-ups building architectures that allow them to scale, right? Usually you build architecture based on the organization. You want to build autonomous teams. And usually if you start with a startup with 20 people, right, everybody can work on the same monolith, but if you have 200, 300, 400 people, it starts to get a little bit messy, and we need to slice out things, and we need to structure them, and that's what I will probably touch a little bit here. So my name is David, happy to be here. Everything else, if something is out of interest for you, or if you want to dig a little bit deeper into some topics, feel free to reach out afterwards, or just write me an email or stuff like this. So a reactive mindset, as already mentioned, I think the most important term is obviously reactivity. Does everybody know what reactivity in the context of programming mean? Obviously not. Are there some Svelte developers? Angular, I guess. So RxJS, right? It's kind of reactivity as first-class citizen. So the Wikipedia definition would be it's programming or designing upon asynchronous data streams. Okay? This is what reactivity means. And the important term is again streams. So another term which needs to be covered. And when I talk to programmers or when I talk to teams, I often have the feeling that streams is such another magic word, right? Streams are everywhere. There's Kafka, there's other streaming systems. And it seems to be very complicated, but it is not. Does anybody have a good explanation how he would explain a stream to his parents or his grandmother? Yeah? Yeah, I guess it's just another data structure, right? I mean, first of all, it's important to understand that everything is a stream, right, these days. So, as always, right, when you start to learn about streams, you will solve every problem with a stream, but you find out that it's not the best solution for everything. But I'm also lecturing at university in Vienna, and there I always need to explain it in a very simple way, right, to young engineers, what a stream is. And I usually do it in this way, that I say, you know, when we talk about data structures in software engineering, then it's basically very simple. This graph now looks much more complex than it actually is, but you have usually two dimensions. You have the dimension of space and you have the dimension of time. And when we say in synchronous time and in singular space, then we tend to have something which we tend to call a value, right? No surprise, it has a getter and a setter, and usually each programming language we use these days supports getters and setters and values, right? If you stay in synchronous time and move to plural space, what we used to have is a collection, right? And the collection usually has an iterator and a generator. Again, each programming language out there has some kind of collections, arrays, linked list, whatever it is ultimately, right? When we now move from synchronous time to asynchronous time, but stay in singular space, then we tend to have something which we call a promise, right? And the promise usually has a deferred and a resolver. And that's already interesting because many programming languages, many ecosystems out there started to adopt promises as first-class citizens, right? So JavaScript was one of the first ones, right? We have them in Spring, in Java we have them in .NET, we have them nearly everywhere, so they seem to be part of languages. And that's the part about streams, right? And you already assume what's on the right-hand side here. It's something which lives in asynchronous time, but lives in plural space, and that's basically a stream. So it's just another data structure which has a subscriber and an emitter. And that's the thing. There's no magic behind streams, right? It's obvious that it existed. It existed forever. The thing, it's not part of most languages, and that's why we introduced like reactive extensions, which basically just move this data structure into our ecosystems. So, as I mentioned, reactivity is about programming designing upon an asynchronous data stream. So we now understand what streams are about, and we will talk about designing, so about the system design later, but I first want to bring you all on the same level. So I would like to talk a little bit about programming. So reactive programming, again, it's very simple, and I explained it, I think, nearly 100 times now, yeah, without over-accelerating. And I always explain it with this super simple example. I guess everybody can read this code, even if it's JavaScript. But we have a counter variable 2 and a double variable which is counter multiplied by 2, right? So what's the value of doubled? Yeah, it's exactly. It's no speciality here, right? So we can assert it and say doubled is 4. Everything fine, cool, great. When we now update our counter to a value 3, right? So first of all, it's a fantastic comment. Updating the counter, setting the counter to 3. And then we could assume that double is 6, right? But obviously it isn't. We all know this, right? Because if we want to have double as 6, we would need to reassign it and would say double is again counter multiplied by 2. And doubled would be 6 then. And that's fine. But that's the criticism of the reactive community of us on this way are we programming, that this relationship between counter and doubled is very implicit, right? It's just something that exists in our head, so we need to take care that whenever we change counter, we also need to update doubled. And probably doubled and counter should be kind of bound, right? So there should be explicit relationship that whenever counter changes, doubled also changes. And there are lots of people who found this out much earlier than me did. And one of them is Paul Stovall. I don't know if you know him, but he has a fantastic blog, and he described a concept which he calls a destiny operator. And the destiny operator is just an abstract concept for now, but we could say, you know, we introduced this thing here. And this is an explicit bounding now from counter to doubled. And whenever we change counter now, in this case we change it to 3, our doubled will automatically be updated to a value called 6. And now it comes back to streams. What has all this to do with streams? Well, you achieve this usually by using streams. So what you would do in reality is you would introduce a stream with an initial value of 2, so counter is 2. would introduce a projection of the existing stream, which is in this case doubled, so counter mapped, and we introduce out of this counter another stream, which we tend to call doubled. And this doubled stream then has a value of 4. And then whenever we update the counter, we will probably just emit a new value to our counter stream, which is 3. This would go into our stream. And without doing anything in addition, our doubled stream will also be updated, right? Because it's just a projection of our counter stream. And then we could basically just assert the doubled value is 6. So we achieved reactive programming by utilizing streams. And this is still pseudocode, but in reality this looks very similar. So I saw a few raised hands when I talked about Angular or RxJS. It looks basically like this, right? You have a behavior subject, it's nothing else than a stream with an initial value. You have a pipe which maps the existing stream into a new stream. We can emit a new value to the counter stream, and basically we can just check the value of doubled and it would be 6. And this test will work, yeah? You can copy this code, put it into your IDE, and it will run. And in more modern frameworks, like for example Svelte, they even took this concept a little bit further, right? We have a counter variable of 2 again, and then we introduce a variable called doubled, which is just counter multiplied by 2. And you see this simple prefix, this dollar, this PHP prefix here, right? And what this says is that we in Svelte now have a reactive value called doubled. And basically what we need to do is now we just set counter to 3, and then we can assert double to be 6. And again, this test will run. So this is already very close to this initial Paul Stovall destiny operator. We just have this small prefix and everything kind of works in the background with streams. And as already mentioned, I think in the intro now, if you want to take more close look at how modern libraries solve these reactivity issues, then take a look at SolidJS. They have a very beautiful implementation of reactivity. So I mentioned I talk about systems, right? I talk about architecture, and that's what I would like to do now, because we can basically apply these concepts of what I just showed you, reactive programming, on systems as well. And hope that this still makes sense, right? But actually we do this quite often. We take a lot of concepts from software design and put them on software architecture and the other way around, right? So if you think about CQS, which is a pattern for software design, we can also apply it on architectural level as CQRS. So very similar. And for reactivity, this seems to be very, very similar. And as I mentioned, I work a lot with, you know, kind of companies which grow very fast and which need to kind of come up with structures that help them to grow. And of course, in many situations, we tend to go for the architectural style of microservices, but doesn't really matter. We don't need to discuss now the concept of microservices. Let's just think about it like another distributed system. And in our use cases, I work a lot in fintech and financial industry. And let's assume a super simple example again, right? Let's assume we have 3 services. We have a user service, we have account service, and we have a ledger service. And then we have a web banking. So you go to web banking from some kind of neobank, and you say, yeah, let's trigger a new payment. So we have 20 euros from David to Lisa, and I perform this payment. So if I click on this button, there will be probably some request to a user service to transfer some money. The user service will make a request to account service to trigger a payment. And from there on, we will go to a ledger service to create a transaction. And this all goes back, and we are done. The payment was successfully executed, right? Sounds fantastic. Unfortunately, that's the happy path, right? In reality, it will never work like this, obviously, in most situations, because probably we have a ledger which is not in such a good mood. And when we talk to the ledger, it just says, you know, it's not my time right now. Give me a call later. And this is, of course, a very bad situation. If you ever transferred money somewhere and you didn't get an answer, or, you know, the system is just in idling mode or just loading, it's actually a very shitty user experience, right? And maybe the ledger returns at some point in time and we say, okay, the payment was still successful, we are not happy with this, right? And we try to solve these issues in distributed systems, right? We try to solve this with retries, what we just heard, with timeouts, with circuit breakers, and all these things. And the important thing, and I think this was also mentioned in the talk before, is we need to synchronize all this stuff, right? Because as it was explained, usually we make retries in an exponential growth. But if one system doesn't do this, right? If one system retries every 10 milliseconds and another one, just retries 10 milliseconds, 100 milliseconds, 5 seconds at some point in time, and the other system still tries to retry every 10 milliseconds, you DDoS your own system. So it's getting very complicated, and it basically just sucks, right? That's the essence of it. And that's what I usually tend to call this first generation of microservices, where we did this whole integration more or less synchronously, and where we ran into this resilience issue that if one service doesn't work, it becomes the bottleneck of the overall system. And what we did then is that we solved this issue, and we solved this issue by actually putting queues in between. So whenever we trigger a transaction now, we put this transaction to a queue, and then we're basically done. Because when we send this request, it's received in the queue, and basically then we can say, the payment was accepted. And that's important now. There's an accepted, right? There's not a created anymore. So we moved from HTTP 201 to HTTP 202. So we told the customer, we got your payment. We will do it at some point in time, but we didn't do it right now. So probably it will take some minutes or seconds or hours, whatever. And the queue will take care of the rest, because the queue bothers the ledger as long as it can until it takes the request, and once it takes a request, it will process it. But if you isolate one bottleneck in your system, by nature you observe the next one, right? So probably the next one is to trigger the payment between the user and the account service, so we can put a queue in between there, and we could put a queue also in between there. And this was the big times of systems like RabbitMQ or ActiveMQ, all these AMQP systems which we utilized to make our system more elastic, to make our architecture more resilient. So this was kind of the second generation of microservices or of distributed systems, which is message-driven and asynchronously integrated. But if you take a look at this, and I often see this, and I most of the time actually see this if I take a look at microservice articles at Medium or stuff like this, but there's a big fat hidden elephant in the room here if you take a look at this, right? Because there's something obviously deeply wrong in this whole architecture. And the first time you will realize this is if you go to your product owner, right? Is some product owner here actually? No, I have assumed this. Product owners don't go to technical conferences anymore, unfortunately. But if you have a product owner, he would probably tell you as a customer, I want my transaction to be booked by the ledger. No, that's what no product owner would ever tell you if it's a good one, right? Because no customer cares about this at all if your transaction is booked on a ledger or somewhere else, right? Maybe he would tell you, as a customer, I want the account service to update my balance. No product owner would ever tell you this, yeah? What a product owner, a good one, would tell you, we have this new fancy feature that the customer wants to transfer money to someone else. That's what a product owner would probably tell you, because that creates customer value. Transferring money from my account to your account. That's what I care about as a customer, not where it's happening. And now we see this issue because this product owner now would need to go to the user service and would say, you know what, we have this new endpoint, somebody calls you to trigger a new payment, can you please extend your endpoint? And then please call the account service. I will just go to the account team and tell them, hey, you know what, you get a request from the user service, please extend your endpoint, and then ultimately put a message in a queue for the ledger system, and hey, please, ledger team, can you pick up this message and, do something with it and process it and finalize this whole customer journey. And we are aware of this, right? So most of the people are kind of aligned on this, that this is an anti-pattern, which we tend to call the entity service anti-pattern. So we shouldn't slice our services based on entities like we do with good old databases, but we should slice them based on customer journeys. And that's a very old idea. If you take a look at the very old papers from Parnas, 1972, he already described that we should not slice systems based on data objects, but based on workflows. He gave them different names, but ultimately he meant the same thing. So we actually just took us 50 years now, right, to really understand this, that we should actually slice our services based on customer journeys. And if you're long enough in software engineering, you know that you can solve every problem with just an additional layer. And that's what we basically did. We just renamed those systems into domain services and put journey services in front of them. Like, for example, the payment journey, which I just told you, which then goes to the user service, account service, and ledger service. And ultimately, if you then talk to your product owner, he will hate you even more because he now needs to go to 4 teams. And even worse, in some situations, people started to put this journey logic into the backend for frontends, right? So we have a web backend for frontend, we have a mobile backend for frontend, and then ultimately they call each other, and they all have this payment flow logic implemented, and if you go to your product owner, he now needs to go to 5 teams. So it's just even getting worse, and I see this a lot. That's why I put it on the slides, because the backend for frontend pattern is a fantastic pattern, but it's not for duplicating logic, right? It's just to avoid overfetching and over-requesting, so we should always be aware of this. But back to our problem. So we have these customer journeys, like, for example, triggering a payment, or let's say checking the current balance, which would probably also need accounts and ledger, or actually, for example, accounts in this case. And that's actually the thing. If you take a look at these customer journeys, you see that the problem is that they both need probably some account data. And that's what I tend to call the customer journey and entity data mismatch problem, which is actually a huge problem. And I will explain you why. Because most systems out there have entities. Actually, not most, all systems have entities, right? Systems have entities like users, accounts, or transactions. And we have customer journeys, like triggering a payment, doing the onboarding of a new customer, or doing some fraud detection. And payments probably needs accounts, transactions, and even users. Onboarding needs users and accounts because it creates a new user, and for this user it also needs to create an account, and fraud detection probably needs accounts and transactions. And you already see the problem. So you cannot have a one-to-one mapping between entities and customer journeys, and that's the so-called entity-customer journey mismatch problem, which actually leads to this effect that, for example, if we have all these interactions between the system, and if our account service goes down, we again have this big problem that probably our whole system is not really replying to us anymore, because everybody needs this account data from our account service. So how can we solve this issue? Well, we could easily just say, we migrate all the data to all the services. So we say onboarding needs user and accounts, payments need user accounts, transactions, fraud detection needs accounts and transactions. So we have full autonomous services. When onboarding breaks, it has no effect on payments. But on the other hand, we also have data duplication. We have accounts now everywhere. And this leads to data synchronization, and that's usually a huge problem. So the first thing we need to always do in distributed systems, and that's something we often forget in the beginning, is to clarify who owns which data. That's the precondition. So in this situation, we could, for example, say, you know what? Users are owned by the onboarding service, and the payment service owns accounts and transactions. And whenever the payment service needs users, it just goes to the onboarding service and asks for them. But then we're back in synchronous calls. And if onboarding service is down, our payment service would probably not work. And of course, we could solve this issue again with user caches and stuff like this. We talked about this. We don't want to have this. So there must be a better solution. And if you took a close look at the slides about reactive programming, then you saw this sentence that we project data from our counter variable into our doubled variable. And this is where all comes together now. Yeah? Because actually we want to do here something very similar. We want to project data from our user. We want to project the user from our onboarding service into our payment service. So we basically want to take the users from our onboarding service and want to push them to our payment service, or project them into our payment service. So in a more domain-driven design terminology, we would say we have a user aggregate on the left-hand side and we have a user read model on the right-hand side. And whenever we change the user aggregate, we have a user change command, and each user change then actually generates a user changed event. And this user changed event then would update the user read model. And that's basically CQS in a nutshell, just as a side note. And we usually do this, as we saw before lunch, with a stream. So could be, for example, Kafka, could be something else. And we trigger this event then to the stream, which is user changed event, and this would then transform the read model, and it will be applied on the read model. And again, there are hundreds of technology you can use. You can use Kafka, you can use Apache Pulsar, you can use kubemq if you are very Kubernetes-centric, or you could, for example, also use some simpler tools like Redis. Doesn't really matter. I prefer to use Kafka, to be honest, but it's up to you. And what we then usually do is that we put all this stuff in a stream, right? So whenever a user gets updated, we put this event into a stream, and we consume this event that the user was updated into our payment service via the stream. And if the user gets updated again, we get another event, and basically we dare put it then into something which we tend to call projections. So these are just simple read models where we materialize the user changed event into a user read model. And we could do this then for everything. We could push whenever a new transaction is triggered, we could push this event to a stream, and we could then, for example, consume them where we want to consume them. And the cool thing, if now onboarding service goes down, there's no problem, because we can still utilize the users from our projection. So we don't need at runtime to directly call from the payment service or onboarding service, because basically we shifted from a pull-based approach to a push-based approach. So we have huge service autonomy here in this situation. And now the classical question comes, and we talked about this after the lunch short presentation of this database system, because I'm always curious then that this actually introduces eventual consistency, right? And everybody is afraid of eventual consistency. But the term eventual consistency is actually a very big one, and I think we need to be clear what we mean by eventual consistency. And I usually differentiate into three things when I talk about eventual consistency. The first one is eventual divergence, which we tend to describe like this. We have a user changed event. For example, the user now got age 21, and we have another changed event, the user got 22. And we could then, for example, say, you know, we have a dashboard and we have a profile service. And the dashboard, for example, could consume the user age 21 event and then could consume the user age 22 event, so the user has an age of 22 in this service. In the profile service, we could say, you know, we, for whatever reason, consume the user changed age 22 event first, and then consume the user changed age 21 event second, and then the user has age of 21. And then we have this kind of eventual divergence, which means that we have the same amount of events, but we have them in a different order. And more systems start to be able to solve this issue by having some ordering guarantees, at least on partition level. And we could simply just solve this by introducing timestamps. So, you know, when I got a later event, and if the event is idempotent, I just skip the older event and everything is solved. So there are ways to definitely solve this problem, but it's something you need to be aware, right? That there is not always an ordering guarantee in such event-based systems. The second one, when I talk about eventual consistency, is usually eventual variance. So we have a stream, the ledger publishes some transaction there, and for whatever reason, this publishing of an event doesn't work. So the ledger retries again, sends it maybe twice because it didn't find out that the first one worked. And then we have a dashboard which consumes this event, and we have a balance of 20 euros there, which is obviously wrong because the user should just have a balance of 10 euros. And that's something we can solve usually with deduplication, but it's again something which happens in event-based systems because usually we just have at least once guarantees there. But what most people, I think, mean when they talk about eventual consistency is actually eventual latency. So we have again these user changed events with the age of 21 and 22. So we consumed them there, and then the second event appears. And the profile service starts to consume this event, and the user age is now 22. But for whatever reason, the dashboard system cannot access the network anymore, has some split brain or whatever, and stays on the age of 21. So there's a latency in communicating these changes to all our systems. And if the user then comes and goes to the dashboard and says, okay, the user has an age of 21, and goes to the profile and says, okay, the user has an age of 22, it says, what a shitty system, right? I have different age on 2 pages of this system. But again, this is something we can usually solve. We cannot fully solve eventual consistency, right? Everybody who's aware of the CAP theory knows that this is kind of a physical problem, actually. But we need to understand that eventual latency is often a problem on user context level. So it's often a problem for me as a single user. If I change my age and then go back to this page again and say, oh, obviously I changed my age, but it isn't reflected here, then it's problematic. But if I change my age and you see it 5 minutes later still as an old age, maybe 5 minutes is a problem, but 5 seconds is usually not. So it's on a single user context level. So we can do a lot of this stuff with front-end caching or optimistic UIs, where we solve this problem actually on the front end of eventual consistency. And basically, these are the three things. So we have eventual divergence, same events but different results. We have eventual variance, same events but different quantity of those events. And we have eventual latency, same events but different realization. And again, we could talk a whole talk about eventual consistency. We could do a whole workshop about it. But there are ways to overcome this. So on the one hand side, we can do ordering guarantees for eventual divergence. We can have at least once delivery and duplication mechanisms, deduplication mechanisms for eventual variance, and we can have kind of optimistic UIs, for example, for eventual latency. So in a nutshell, that too long don't read, eventual consistency is often used as a knockout argument if you talk to architects, or especially if you talk to business, but usually it is not. Yeah? We can usually solve it. Of course, there's a trade-off and we might need to find a sweet spot, but usually we can find a sweet spot which allows us to be our system in a reactive way and have maybe some little eventual consistency there. So with our projection, as we mentioned, we have a super highly autonomous system. And I give you now a real-world example. So I worked, I think, 8 or 9 years ago already for a German bank, and this was the time when N26 and other, challenger banks started to start their business. And this bank decided to also build a total new mobile banking application. And it was kind of interesting because we did something which was back then very unfamiliar, and I think is these days still too unfamiliar for many big projects, but we wanted to understand what customers actually need from us, right? And we did some research, and we found actually out that 93% of all those customers of these mobile banking applications basically just take a look at the current balance and the latest transactions. And maybe you re-see yourself there, right? You take out the phone, check, okay, I have enough money, all good. Let's go drinking. And 3% of all other users initiate a new payment, and 4% is something else like locking a card or so. And I always say these numbers are interesting for various reasons. That's interesting from an HR perspective, because if you talk to me back then, and if I was working on the system, I invested, I don't know, 6 months in this fucked up card locking feature because it's super complicated, but nobody ever uses it, right? It would have been much better if I tweak out the best UX and the best performance for showing the latest balance and the latest transactions. And if you know this kind of non-functional requirements, you can tweak your architecture in a way that you achieve them. And that's basically what I mean when I talk about architecture. Architecture is not a context-less zone, right? You always need to understand what are you doing. And if you build a system like this, where 93% of the users just want to see latest transaction, latest balance, then you can easily achieve this with reactive architectures. Because, as we said, user triggers a transaction, this transaction is pushed to a stream, somebody consumes it, puts it into projection, and bam, we can, from this projection, read it in our web banking application. And we can start to burn things. We can start to burn the onboarding service. We can start to burn the payment service. We can even start to burn our Kafka stream. And we can still achieve that 93% of our users can do what they actually wanted to, right? And that's fantastic. That's amazing, actually. And this is what this architecture gives you, high resilience, right, in distributed systems. And even if you have high loads, we can easily do this, because we can just spin up a second service, basically spin up a second projection, so we'll consume these events again and build the suite model again. And we can then, take one of those two overview services to fetch our systems, our transactions, and if one of them fails, we can, again, easily horizontally scale, right? So reactive architectures allow you to easily horizontally scale services, and that's another fantastic advantage. And another one, when you trigger new payments, and if you go, to the payment service, trigger a transaction there, put it in a stream, consume it in projection, and then basically stream it through, then you can actually achieve these real-time capabilities. And what we often then actually do is, so what you just saw is you got a transaction and you updated the balance without pressing F5 or reloading the page. And what we actually then often use is Graphql, because Graphql is fantastic for reactive systems, and Graphql has a lot of cool features. But one of the best one for me back then, at least, was that it treated subscriptions as first-class citizens. So you know, it's just like a queue, just a different keyword, and you can build this beautiful end-to-end reactive systems beautifully with GraphQL. So if you build GraphQL systems, I always say that the most beauty you get of them if you just use subscriptions and mutations, because then you're fully reactive, right? A queue is an anti-pattern. No, it's just a joke, but makes totally sense if you go into this direction. So we have out-of-the-box real-time capabilities. We don't need to build this stuff afterwards because our system is push-based. We get changes all the time pushed into our system. We don't ask for them. We don't need to pull for it. And another advantage is, of course, working with legacy systems. We all know working with legacy systems is super tough, is super annoying, and makes no fun at all. But sometimes we need to do it still, right? And the problem is that the legacy systems are actually not most of the time the issue. The problem are really the legacy databases. So they are really hard to decompose. And if you think of legacy database systems, they usually have a user in there. And we can, for example, use change data capture to just stream these changes on our legacy database into our stream and then consume them, and then make at least our new services independent of this old legacy stuff. And that's basically the third generation of microservices, to build reactive, to build them upon on reactive data streams, which makes them high resilient, horizontally scalable, allows us to give real-time integration very well, and also even supports us for legacy systems. Again, very high level, yeah, we could go into detail here everywhere. But I brought you something special because I brought you the last generation, which I see of distributed systems, which even goes more into this direction. And when we talk about scaling, we often see two dimensions, right? We see vertical and horizontal scaling, and we are all aware of this, right? So you can push a service up, so you put more memory, you put more space, you put more disk into it. But this is actually very cost efficient, especially in the cloud. So we tended to go for horizontal scaling. So instead of one instance, we have 3 instances, and we can easily start them, close them, so we have more elastic for various load. But the problem, which I told you before, is that in an optimal world, we would have a projection on all of the service instances. So everybody would consume the stream and would, for example, build up a user projection. But in reality, this is much more complex because hydrating these projections usually takes a lot of time in the service, in the beginning of the service, and that's actually something we want to avoid. And in addition, we would need to go for an event-sourced system that this really works. So what we often end up is that we have a shared projection for multiple service instances. But again, this can become a bottleneck because at some point in time, always the database usually is the bottleneck. And that's why there's a third dimension of scaling, and that's something we tend to call sharding. So we could also shard our services, which basically means we just group them. We, for example, group them based on user groups, or we group them based on user countries. So users from different countries run on different services, and then we can easily say each of these services has its own projection because it just needs to build up the projections for the specific user group. And we could even combine them. We could even have sharded horizontally scaled services. And how does this look like? So for example, in our case, we can say this user triggered a payment, and this user triggered payment goes into a stream. And let's assume this user is, for example, from Great Britain. So we push it into our first shard. So in this case, in Kafka, for example, it would be our first partition. And then we push it there, and then, you know, we have some instances of the payment service running there. One of them for an explicit shard. We consume them, push them to the next shard, and so on and so forth. I'm running a little bit out of time, so I'm doing this a little bit faster now. And in the end, you know, we actually end in the ledger, and this ledger then puts the transaction in the shard again for Great Britain users. So we have fully independent shards. And as I mentioned before, this makes this whole concept of projecting data much easier because we can stay with this projection in our shard. So partition 2, our second shard, would just, you know, project all the transactions of this shard into the fraud projection, in the fraud detection projection, because we just need the payments, for example, from British users there. And we then can kind of have these isolated projections which make our systems then much faster in scaling up. And this is what we usually tend to call streaming, and this is where we use technologies like Apache Flink or Kafka Streams. And in the end, we can just push all this to a sharded system, which allows us to easily read this, like, for example, Elasticsearch, which internally uses shards. and then we can actually even have dedicated UIs for each shard, so we have a full sharded system, and then just, you know, can push millions of transactions through the systems. Yeah, I always say you cannot break the system. I'm sure you can, but I in reality never saw that we were coming to a limit for those systems, for fully stream-based sharded systems. So we built banking engines which usually really have multiple transactions per second or millions of transactions per day, and there's no way to break this. Yeah, we can have 24 shards. So in the system I worked, we had 64 shards, right? So 64 shards based on users, and actually you have 64 instances, so you can never kill this system. And that's fantastic because we have, yeah, nearly unlimited scale, and that's the kind of last generation of microservices of distributed systems which I see. It's sharded and fully stream-based, and this gives us, of course, massive throughput and extreme scalability. So as always, many choices. Let's sum up all this stuff. Yeah, what I told you now. So I started to give you an overview what a stream is. This was, I guess, very simple, but I guess important. And then we talked a little bit about reactive programming, and we took the same concepts and put them on system level. And I missed something which is very important to me, which is the monolith, right? And it's a pity that I missed it because I love the monolith. I would always go with a monolith. I'm a big relationship with monoliths. So stay as long as possible on the monolith, right? So if you, I don't know, 15 people, stay with a monolith. Yeah, start to split up if it really doesn't work anymore differently. And if you then think you can split it up in the synchronous way which I showed you, we will just have pain. You will have sleepless nights and pain. So don't do it, yeah? Go back to a monolith, start to shuffle things around, that still multiple teams can work on a single code base. And if at some point in time you really need to have different deployment units because you want to have teams to be independent, deployable and stuff like this, then you need to split it up, but then do it in an asynchronous way. So when you do this, you will find out that you need to share a lot of data. And you will find out that this pool-based approach for data sharing sucks. And you will need to spin this anywhere around. So you will go from a pool-based to a push-based system, and this is where you land actually in reactive systems. And if this is still not enough, then you can go with sharded and stream-based systems where you really have massive throughput. But again, you can see from the left-hand side to the right-hand side all these different approaches. And those different architectures, as always, buy you features. They give you this availability, resilience, scalability, throughput, all these non-functional requirements which we are all striving for. And the more you go to the right-hand side, the more you get of those features. But those features are not for free, right? In architecture, we always pay for features. And the currency we pay them is complexity, right? So, of course, also the complexity increases to the right-hand side. So the important part is that you find the sweet spot, right? You need to find the spot where you say, you know what, I just need better resilience, so maybe an asynchronous integrated system is already enough. I don't need a fully stream-based system. So again, it's important to understand for us when we come up with architectures, what are the non-functional requirements, basically those things at the bottom, and how much do we want to pay for them? So I can only, just as an advice, stay as long as possible on the left-hand side and go as slow as possible to the right-hand side because it will make things super complex. This was it. I hope this was useful. Thanks a lot. I'm here till the after party or even longer, so if you have some questions, feel free to.
Thanks a lot, David. Thanks a lot. What a great talk. It's time for questions. Anyone have questions? If you have, show me your hands. There we go.
When you were switching to streaming, you left out all these two implementations. Purpose or is this implement the streaming part with revenue, for instance?
You can repeat his question first, just for the live stream.
If you cannot utilize IMQB systems like RabbitMQ for streaming, yeah. Well, what's the difference between streaming and queuing? The thing is that the one has at least short-time persistence and the other one hasn't. So if you have a RabbitMQ and consume the message once, it's more or less gone, right? And the problem is in stream-based system or horizontally scaled systems, this is not allowed to be the case because you can spin up new instances and they kind of need to replay those events to build up their projection again. So we need this kind of possibility to have long time persistence in our queues, and that's actually what differentiates stream-based or a streaming platform from a queuing platform, right? So of course you could probably do it. No, you cannot do it. It's, you know, for example, some queues already have kind of support for this, right? And the difference between a stream and a queue is kind of getting a little bit fuzzy. That's why, I mean, you can probably also achieve it with queues, but these queues already then use kind of some persistence. Yeah.
Great. We're gonna leave that there, the questions, because we're quite behind schedule. But let's hear it one more time for David, everybody.